Hello everyone. In this video, we're going to see how we can trap rainwater. The algorithm in this video is important. You can use it if someday you get stuck in the desert and you need to trap some water to survive. So we are given an array of positive integers which represent an elevation map. The width of each of the bars of the elevation map is equal to 1. We should compute how much water this map can trap after raining. So this is the input array. Each number right here represents the height of these black bars. So 0 here means this one has a height of 0 and width of 1. The second bar has a height, as you can see here, of 1 and the width is equal to 1. The third bar has a height of 0 and width equal to 1. This bar has a height equal to 2, as you can see, and width equal to 1. So this structure can trap water between its bars. We should calculate how much amount of water it can trap. Each square right here, if it's free and it's not filled by the black bars, and if it can trap water, then it will trap 1 unit of water. So for example, here we have this 1 unit, and here you have 1, 2, 3, and 4 units, and here you have 1 unit, so the total will be 6 units, and this will be the answer. So let's go to the canvas and discuss this problem. So let's try first to find the most intuitive approach. How do we know, if looking at some square, that we can trap a drop of water inside it or not? So first of all, we need to have a bar to the left and a bar to the right, and we can draw a line of height equal to the height of the smaller bar, and then under this line, all the free space, we can trap water in it. So for example, for this bar and for this bar, we can draw a line equal to the height of the smaller bar, which is this one, and then under this line, we can trap water. Similarly, for this bar and for this bar, we can draw a line equal to the height of the lower bar, and then under this line, in all the free spaces, we can trap water. So under this line, we cannot trap water here and we cannot trap water here because these are not free spaces, but we can trap water here and here and here and here. So these are 4 drops. Also between this bar and this bar, which have equal heights, we can draw a line between them and we can trap water under this line in all the free spaces. We cannot trap water right here because this is not a free space. So this gives us an idea of how we can solve this problem. We can, for example, start iterating through the array or through the elevation map, because the elevation map is representing the array. So we can start iterating here. If we start at the first index right here, we cannot trap anything at the first index, because even if we have a bar right here, to our left we do not have anything, so the water will just come and spoil outside. So we can skip the first index and we can come here. Here we will find that we have a bar with height equal to 1. We continue our search to the right and we will find a bar right here with height equal to 2. We can draw the imaginary line we talked about right here, and then for each of the indices between this bar and this bar, we can calculate the number of drops of rainwater that we can trap. The formula will be hi, because I is the smaller index, or let's call it h small, smaller height, minus hk, where k is the iterator that iterates over all the indices between the small bar and the tall bar. So at each index between the small bar and the tall bar, for example at this index, the amount of water that we can trap here is equal to this formula. which is height of the small bar minus the height at the current index. So for example, right here, h small minus hk, it will be equal to 1, which is the height of the smaller bar, minus the current height, which is 0, it's equal to 1 drop. If we take another example, so let me clear this up. If we take I is here, and we keep searching, and we find this bar right here, so we can draw an imaginary line between these two bars. And if you are wondering why I stopped at this J right here and I did not stop, for example, right here, well, because when I started at this bar, I keep searching to the right until I find a bar that have a height equal or larger than this one here. In this case, I can draw an imaginary line and calculate the number of drops of rainwater. Because, for example, if we have this structure like this, if we are going to the right, we cannot find any bar that has a height equal or larger than this bar. So we cannot draw an imaginary line of this height. We need to draw an imaginary line of a lower height. And we will talk about this later. So continuing our example here, under this line, we can calculate the number of drops that we can trap. So for example, at this index, and remember that h small in this case is equal to 2. At this index, the amount of water that we can trap is h small, which is 2, minus the current height, which is the height at the current index, which is this one right here, from here to here, which is equal to 1, so equal 1 drop. If you look at this height, the height here is equal to 0, so minus 0, and we have h small, which is still equal to 2, so we have 2 drops of water right here that we can trap. If you look here, we have h small, which is 2, minus the height, which is 1, so we have 1 drop of water that we can trap. If we continue by this manner, now we will get I to the position of a j and start again searching. So now our height is this one, initial height, and we are searching for a height that is equal or larger than this height, so that we can be sure that we can draw a line like this one and trap the water under this line. But as you can see right here, that starting from this position onwards, there is no other bar that has the same height as this bar or larger. So we cannot draw an imaginary line and say, for example, let me show you what I mean. If we now draw an imaginary line, even though we did not find any bar that has a height equal or larger than this bar right here, so if we draw this imaginary line and we try to calculate the amount of water, for example here, that we can trap, the formula tells us it's hi, or the height at the smaller bar, which we assume that this is it, because we did not find another bar that has a height equal or larger than this bar, so we will assume that this is the bar with the smaller height. So h small is equal to hi, so the amount of water that we can trap here at this index is equal to hi minus the height at the current index, which is 2, so it's equal to 3 minus 2, it's equal to 1 drop. So this formula now gives us a wrong answer. It tells us that we can trap 1 drop of water here. But if we look at the diagram, this drop of water right here has nothing to support it from this side. So it will spoil outside. So this formula will not work for this column. So what we should do is stop and advance I by 1 to see if we can find another bar that has a support to its right. So if we advance I like I did like now, we can go to the right. Is this bar has a height larger than or equal the bar at I? No. Here, does this bar has a height larger than or equal the bar at I? Yes. So that we put J right here and we draw the imaginary line, and then between them we can calculate the amount of water that we can trap. And then we move I to the position of J, so right here, and we start searching to the right. Again, we will try this bar, it has a lower height. And then we will try this bar right here, but now we are outside the bounds of the array, so we can stop. So this algorithm will work and will solve the problem, but it is not optimal. Why? Because let's say that we have this structure. So we have initially this bar, and then we have a smaller bar, and then we have a smaller and smaller and smaller, and this bar. So initially we will stand here, and we are trying to find a bar from this side that has a height equal or larger than this initial bar that we are standing on. But the problem is that we are not searching from the right. We are searching by this direction. So we will need to go over this bar and this and this and this and this. And then we go outside the bounds of the array until we discover that there are no other bars that have the same height or larger than this bar. So in this case, we will advance I to the right because just before advancing I, because if we do not advance I, we cannot draw an imaginary line and assume that we can trap water under this line, because we did not find any bar that can support this line from the right, because no bar has a height equal or larger than this bar in order to support this imaginary line from the right. So what should we do in this case? We should advance I by one position and then try the algorithm again. In this case, the algorithm will also reach the end of the array so that it discovers that there are no bars equal or larger to the height of this bar. So we will advance I again and repeat the same process. And as you can notice, for each one of the bars, we are iterating over the whole array. So the time complexity of this algorithm will be O(n) square, which is not optimal at all. So let's try to find another optimal approach. And let's start finding our optimal approach from the place where we ended this discussing this non-optimal approach. So why is this approach non-optimal? First of all, let's take back I and put it at the first index. So what are we searching for? We are searching for a bar from the right side. From here, we are searching for a bar from the right side which has a height that is equal or larger than this bar at I. Why are we doing this? Because we want this bar from the right to be supporting this bar from the left. So we want some bar right here to be supporting this bar in order to draw this line and be sure that we can trap water between these two bars. But the problem in the first approach that we were searching for this bar here, if it exists, we were searching for it from the right. What if we initially have a pointer pointing to this bar, which we already have right now in the first algorithm, but what if in this second algorithm we also have a pointer pointing to the end of the array? So let me give another example. Let me first of all clear this example. Let's say that we have this elevation map, right? Like this. We have here a bar, and we have like some bar which is tall right here, and we have like a bar right here. So what if at the start of the algorithm we have a pointer called L for left, which we are putting at the first index of the elevation map, and a pointer to the last index, which is called right, R for right. So if we ignore this bar initially, And look at this bar and this bar. We can notice that since they have different heights, then of course we can draw a line between them and trap some water, right? Okay, so let's draw this imaginary line. So we are sure, for now, we are sure, regardless whether there is a bar here or not, we are sure that under this line, in all the free spaces, we can trap water. So this line that we drew right here, its height is determined by what? Its height is determined by the height of the smaller bar, because we're looking at this bar and we're looking at this bar. So the height of this line, which we can trap water under it, is determined by the height of the lower bar. So we will start processing the lower bar. What do I mean? We will draw this line, this imaginary line, and we know that we can trap water under this line. So we will start a variable called k. It will start from here, one index before the right index, and at each index, it's going to calculate the amount of water that we can trap under the line. Let me even put some more bars to make this even more covering all the cases. So just let me clear this up a little bit. Let's suppose that this is an index and this is an index and this is an index and this is an index. Let's suppose that here we also have a bar, and maybe even here we have a bar. So here we can trap one drop, here one drop, two drops, three drops. And let's say that here also we have this elevation, and here we don't have anything. So here we can store these drops. So 1k is one position before R. So to re-summarize what we did from the beginning, at the beginning of the algorithm, we are standing here, we are looking at the right and we are looking at the left. We found that at the right we have this height and at the left we have this height. Regardless of what is between these two, we can draw a line equal to the height of the smaller bar, and we are sure that for every position that is free below this line, we can trap water inside it, regardless of what's between these two bars. So because this is the lower bar, we are going to start to calculate the amount of water that we can trap starting from this bar with the lower height. Why don't we start from this bar? Because if we start from this bar, the formula that we are going to use is for each index. So let me clear this up a little bit. So the formula is, I will write it here. So for index I, amount of water we can trap is equal to height of small bar minus hi, which is the height at the current index. So let me call this I. No need to call it k, okay, just to be consistent with the formula. So we start from the bar with a small height and we start one index before it. And for this index right here, the amount of water that we can trap, as you can see, it's equal hr, which is h right, minus hi, so it's equal to one drop of water, as you can see in the diagram. And then we say I minus minus, so we go to the left by one position, and we calculate at this index the amount of water that we can trap. So I will track the answer right here. So I will put this one here and erase it. So this one is now in the answer. And now at this current index, the amount of water is hr minus hi, and we are sure always for now that hr is larger than h at the current index. So this height is larger than this height, which is 0. So here we can trap 2, so we bring this 2 to the answer, and then we reset it and we bring I here. So as long as the current index I has a height less than the bar to the right, then we are sure that we are still good to go and we can trap water, because if this bar is less than this bar in height, then this bar is also less than this bar, because this bar is the tallest bar. So we are sure, in other words, if this bar is less than this bar, we are sure that we are still under this line. Okay? So we keep repeating and calculating at each index. So at this index, we can trap 1 drop of water. So we add it to the answer, and then we get I here. So I is now here. Okay, now what happens? Now we are at this bar, and this is the line. So now we cannot trap any water anymore between this bar and this bar. What I mean, in other words, is that this bar has become above the line. So this bar has become taller than this bar because it has become above the line. And remember that the line is equal to the height of this bar right here. So what we should do now is we should remove this right from here and put it here. And then we start our algorithm again, but now we consider that the input array is from this left to this right. And then we start the algorithm again. What should we do? We should compare the height of this bar to the height of this bar. Which one is smaller? This one right here. So we draw the imaginary line equal to its height. And now we are sure that under this line, we can trap water in the free spaces. So what should we do? We should start iterating from the smaller bar. So we start I is here, and we calculate the amount of water that we can store at this index, which will be equal to 2 drops. So here we add 2 drops, and then we advance I. So I is now here, and the amount of water we can trap here is also 2 drops. So we put a 2 again, so plus 2. And then we advance I and check the amount of water that we can trap here. Remember, this is a bar of height equal to 1. So we have only 1 drop to store here, so plus 1. And then we advance I. And now I is equal to R. What does this mean? This means that we have covered all the input array. Not this, I mean all of the input array, the original input array. So now the question is solved. And what is the time complexity of this approach? As you have seen, we are iterating over each position only once. So the worst time complexity for this approach is O of n. And the space complexity, of course, is O of 1 because we are not using any extra arrays or data structures. So let's implement this algorithm. Let me clear this up a little bit. And let's implement the algorithm right here on the diagram. So initially, what did we do? How do we think about implementing this algorithm? Initially, we were looking at the left and we were looking at the right. So we will need pointers L equal to index 0 and right equal to index n minus 1, which is the last index in the array. So by saying this, as if we are saying that we are looking at this index and this index. By looking, we mean that we have pointers to these indices and we can access the values at them in the input array. And now what we do is, while left is less than right, because we do not want left and right to pass each other. I mean, if we move left, because as you saw that in the algorithm, we move the right and we move the left pointers under some conditions. So when they meet or when someone passes over the other, we should stop. So while left is less than right, what should we do? Initially, right here, what did we do? We compared the height here and the height here. So if the height at right is less than or equal height at left, what did we do? So we defined a pointer called I. So we said I equal right minus 1, and while I was strictly larger than left, so we do not want I to touch left, and while the height at I was less than or equal the height at R. What did we do every time? We added to the answer the amount of water that we can trap, which is determined by the formula height of the smaller bar, which is R in this case, minus the height at the current index. And of course, we should say I minus minus because we want to move I to the left. And what happens after this while? After this while is done, we should move R, the right, to the position where I is now. So here if we look at the diagram, I was initially here, and then will become here, and then will become here, and then it will become here. When it becomes here, this condition right here, hi less than or equal hr, is no longer true. So what we do is we get out of the while loop and set r equal to I. So let's set it now. So r is here and I is gone. And now we get to the while and we do the algorithm again. So while left is less than right, we compare the left and right again because we changed the position of the right. So is this condition correct? Is hr less than hl, height to the right, less than height to the left? No, the right is larger than the left. So we should put an else. So else meaning the height to the right is strictly larger than height to the left. What should we do in this case? As we discussed, we will put the iterator next to the bar with the lower height, which is the left in this case. So I will be equal to left plus 1. So while I does not touch right, which means less than right, and height at I, as you can see here, in order to be able to trap water, the height at I must be below this line, so it must be below, sorry, not this line, it's this line. So it must be below the height of the smaller bar, which is L. So while I does not touch the right here, and the height at I is smaller than or equal the height at left, what should we do? In each step, we should add to the answer the amount of water that we can trap, which is height of small index minus the height at current index, and we should advance I to the right. So we say I plus plus, not I minus minus. And then when the while is gone right here, we should move the left and put it equal to I. And this will be the whole algorithm. So let's go and write it on Leetcode. So I will be copy pasting the algorithm. So let's say n it's equal to height size, just to make the variables have the same name as in the algorithm. Left equal to 0, right equal m minus 1, and star h equal height. I just changed the name of the array to make the code less verbose. So as we said, while left is less than right, what we should do is we should compare if h of r, I'm just copy pasting the algorithm, is less than or equal h of l. In this case, we define I is equal to right minus 1, and while I is larger than left, and height at I is less than or equal height of R, we should add to the answer the amount of water that we can trap at index I, and we advance I to the left, and then at the end we set R equal to I. And in the second case, which means if h of R is larger than h of L, in this case we are going to set I is equal to left plus 1, so one position to the right of the left index, and while I is less than the right and the height of I is less than or equal the height at the left. So we should add to the answer the amount of water that we can trap, which is height of the smaller bar, which is h of L, minus the height at the current index, which is h of I. And then we advance I one position to the right. Let me just indent these. And then we set L equal to I, so we moved the left pointer. And finally we return the answer. And before running this, just let me tell you that this will even work if the initial left index has a height equal to 0. So let's go to the canvas and let me show you how it will work. So initially in the given example, so left will be here and right will be here. So we will compare, is h of r less than h of left? No. So we will come to the else, because h of left is less than h of r. So I is equal to L plus 1. So I will be here. And while I less than r, okay, it's correct. And hi less than hl. Hi, is it less than hl? This is hi. It's equal to 1. hl is equal to 0. So we will not enter this while. We will immediately come here. So L equal to I. So this algorithm immediately skips the bars with the heights which are equal to 0. So left is now here and right is now here. Now left and right have equal heights. So we draw this imaginary line, and as you can see in the algorithm, hr is less than or equal h right. So we start I equal r minus 1. So I will start from here and we will start calculating. Here at this index I, is it larger than left? Yes. But is it less than hr in height? No. So I will become, so r will become here. We will not enter this loop, this while loop, and immediately we will set r equal to I. And now we will come to this loop again. So we will do the comparison. So which is smaller than the other? The left is smaller than the right. So we enter this loop, I equal L plus 1. So I will be here. And now, while I less than R, okay, and HI less than HL. So this is HI equal to 0 and this HL equal to 1. So here we will enter this loop and we will add to the answer HL minus HI. So HI is equal to 0, HL is equal to 1. So we will add 1 to the answer, which is correct because here we have one drop. And we will keep repeating this loop and this outer loop until we finish the algorithm. So let's try to run our algorithm. And we have a compilation error because we did not define the variable called answer. Let's try again. And it succeeded, and let's submit it and hopefully it succeeds from the first time. And as you can see, it beats 100% of the runtimes and 72% of the memory. So that's it for this video. Thank you very much for watching. See you in the next video. Bye bye.